let us start our class. We are going to study the lesson Electromagnetic Induction. We are going to study the lesson Electromagnetic Induction. This is our second class. In the previous class, we studied about this experiment, isn't it? In the previous class, we studied about this experiment. I think all of you understood well. Next, we are going to discuss which are the factors that affect the induced current. Which are the factors that affect the induced EMF? We discussed about it a little. We are going to discuss about it more. Okay? We repeat the experiment using magnets of greater strength and increase the number of turns of the solenoid. You saw a video, isn't it? On the basis of the experiment, we are going to complete the table. If we increase the number of turns of this solenoid, what will happen to the induced current? It increases, isn't it? Yes. If we use strong magnet, then what happens? Then also deflection of galvanometer increases, isn't it? Yes. If we move magnet with a greater speed, we move magnet with more speed, then what happens? That time also induced EMF increases, induced current increases, isn't it? If we move solenoid with a greater speed, if we move the solenoid with a greater speed, that time also what happens? Deflection of galvanometer increases. In the previous class we studied about it, isn't it? So we increase the number of turns of the solenoid, that time the induced EMF increases. If we use the strong magnet, that time also deflection of galvanometer increases. If we move the magnet or solenoid with a greater speed, with a more speed, then what happens? That time also deflection of galvanometer increases. Okay? So, on the basis of the experiment and analysis of the table, we are going to find out the answers to the following questions. And we are going to write in your science diary. I think all of you write this in science diary. I told you about this. We can discuss today in this class. Okay? Why did the galvanometer needed deflect in the experiment? What is the reason for a deflection of this galvanometer? All of you know this galvanometer is used for measuring small current. It is used for detecting the presence of small current. While moving this magnet and solenoid, if we move this magnet into the solenoid, then what happens? A small current is produced there. Due to this small current, what happens? This galvanometer deflects. And EMF is induced there. Due to the interaction between this magnet and solenoid, an EMF is induced there. Due to that, what happens? An induced EMF. Due to that, what happens? Galvanometer needle deflects. Isn't it? Yes. So, what is the reason? Why did the galvanometer needle deflect in the experiment? What is the reason? Due to the flow of current. In our experiment, a current produces. Due to that presence of current, galvanometer needle deflects. Which are the instances in which there was flow of current through the solenoid? In which of the time there was a flow of current through the solenoid? When we move the magnet into the coil. While inserting into the coil, when we insert the magnet into the coil, that time what happens? Galvanometer shows deflection. Galvanometer shows deflection. If we are taking out the magnet from the solenoid, if we are taking the magnet from the solenoid, if we are taking the magnet out of the solenoid, that time also galvanometer shows deflection. That time also galvanometer shows deflection. If we use strong magnet, then what happens? Galvanometer needle increases. The deflection of galvanometer needle increases. If we move the magnet with the greater speed, then there will be flow of current. If we move the magnet into the solenoid, there will be a flow of current. Instead of magnet, we can move the solenoid. Instead of magnet, we can move the solenoid. We can keep the magnet as stationary and we can move the solenoid into the magnet. We can insert the solenoid into the magnet. That time also what happens? Current is produced. Which were the instances in which the current is increased? Yes, if we increase the number of turns, deflection increases. It shows that current increases. Induced EMF increases. If we use strong magnet, that time also deflection of galvanometer increases. This increased deflection shows that more current is produced there. If we use strong magnet, what happens? Deflection of galvanometer increases, isn't it? This shows that induced current increases. Induced EMF increases. If we use magnet or solenoid, if we move magnet or solenoid with greater speed, if we move magnet or solenoid with greater speed, if we are keeping the magnet stationary, then we are going to move the solenoid with greater speed. We are inserting the solenoid into the magnet. Then what happens? With the greater speed, then what happens? Yes, deflection of galvanometer increases. If we kept the solenoid stationary instead of magnet, if we kept the solenoid stationary, and we are going to insert this magnet into the solenoid with the greater speed, that time also deflection increases. This increased deflection shows that more current is produced there, more EMF is produced there, isn't it? We are going to proceed to the next part. We are going to study about electromagnetic induction. We can discuss about electromagnetic induction a little later. We studied that. Now we studied that whenever there is a relative motion between magnet and solenoid, there is a flow of current. There is a flow of electricity. Electricity is produced due to the interaction between magnet and solenoid, isn't it? If you magnet into the solenoid, then what happens? A small current is produced. Instead of magnet, we can move the solenoid into the magnet by keeping the magnet stationary. That is also a small current produced, isn't it? So from this experiment, we can understand that we can produce current. This was discovered by Michael Faraday. Okay, very good. We have understood from this experiment, there is due to the relative motion between magnet and solenoid, there will be flow of current. A current is produced and EMF is produced. But have you ever thought about what happens when the magnet is brought near or moved away from the solenoid? Here, magnet is near the solenoid. Here, magnet is near the solenoid in figure 3.2a. But in the figure 3.2b, The magnet is inside the solenoid. It is moving. Magnet is moving inside the solenoid. These are the two stages of our experiment. These are the two stages of our experiment. In the first experiment, magnet is near the solenoid. In the second experiment, magnet is moving into the solenoid. Moving into the solenoid. In both times, there will be deflection. The galvanometer shows deflection. You can understand from the picture. The galvanometer shows deflection. Okay? By using this picture, we are going to answer some questions in our test. On which instance will the magnetic flux linked with the solenoid be less? In the first case or second case? Yes. In the first case. In the figure 3.2a. Isn't it? In the figure 3.2a. In 3.2a, the induced EMF or induced current will be less because magnet is away from the solenoid. Isn't it? But in the second picture, the magnet is inside the solenoid. Magnet is moving into the solenoid. Magnet is moving into the solenoid. So, the galvanometer shows more deflection. So, we can say again, on which instant will the magnetic flux linked with the solenoid be less? In the first case, in the figure 3.2. Isn't it? Yes. In the second case, on which instance will the magnetic flux linked with the solenoid be greater? The second case, because magnet is moving into the solenoid. Isn't it? Yes. So, when the magnet and solenoid come together, then what happens? If both are approaching more, then what happens? Deflection of galvanometer increases. Isn't it? Yes. If both are away from each other, then what happens? If they approach each other, deflection increases. If they are away from each other, deflection reduces. So, if the magnet is away from the solenoid, galvanometer shows less deflection. If the magnet is near the solenoid or in the solenoid, when the magnet is moving, if it is stationary, there will not be any deflection. Don't forget about it. So, the magnet is moving into the solenoid. Then what happens? Deflection increases. That is, when the magnet is moving towards the solenoid, deflection of the galvanometer increases. Isn't it? Next. So, in the figure 2, magnet is approaching. Magnet is moving into the solenoid. It is moving. So, there will be deflection. Galvanometer shows deflection. For which instance does a change in magnetic flux linked with the solenoid occur? When it is moving, when the magnet is moving or when the magnet is not moving? Yes, while it is moving. On which instance does a change in magnetic flux linked with the solenoid occur? While it is moving. Yes, from this experiment, we understood that an induced EMF or induced current is induced in the solenoid in relation to this magnet and solenoid. Isn't it? So, we can understand that electricity is induced in a solenoid whenever there is a change in the magnetic flux linked with the solenoid. When this magnet is approaching the solenoid, when this magnet is inside the solenoid, when it is moving, a change in magnetic flux occurs. A variation in the magnetic flux occurs. Due to this variation of magnetic flux, magnetic field lines, an induced EMF is induced. An induced current is induced. Due to that induced current or induced EMF, galvanometer shows deflection. we can say this phenomenon as electromagnetic induction. We can say this phenomenon as electromagnetic induction. The current thus induced is called induced current. The current thus induced is called induced current. We already told that an induced EMF is induced there. So that voltage, that induced EMF is called induced EMF. And voltage is induced there. So that voltage is called induced EMF. Can you say what may be the factors that affect in the induced EMF? Yes, if the number of turns of the coil increases, then what happens? Induced EMF or induced current increases. If we use strong magnet, the magnetic field increases. That time also induced current or induced EMF increases. If we are moving this magnet or solenoid with greater speed, that time also induced current or induced EMF increases. So we can conclude that whenever there is a change in the magnetic flux linked with a coil, an EMF is induced in the coil. Whenever there is a change in the magnetic flux linked with the solenoidal changes, an EMF is induced in this coil. This phenomenon is electromagnetic induction. This was discovered by our Michael Faraday. Okay. If Michael Faraday was not born, sometimes there may be the production of current. Sometimes we had to live without current. We had to live in a world of without current. In a world there was no current. Okay? Yes. So now we studied out the phenomenon electromagnetic induction. Can you say which are the factors on which the direction of induced current in electromagnetic induction depends? In our previous class, we told that when the north pole of the magnet is moved into the solenoid, galvanometer shows deflection. If we move the south pole instead of north pole, this directional deflection changes. Isn't it? We discussed about it in previous class. Okay. So, which are the factors on which the direction of induced current in electromagnetic induction depend? Yes, direction of magnetic field. If we change the direction of magnetic field, if we change the north pole to south pole, then what happens? Yes, if you are inserting south pole into the solenoid instead of north pole, then what happens? Direction of induced EMF changes. Direction of deflection of galvanometer changes. So one of the factors that influence the induced EMF in electromagnetic induction is direction of magnetic field. This direction of magnetic field is assumed to be from north pole to the south pole. So we can conclude what we studied today by using slides. Okay. We are studying the lesson electromagnetic induction. That is lesson 3. It is our second class. Galvanometer needed deflect due to the flow of current, due to the production of current in relation to the magnet and solenoid. Current produces in the solenoid when the magnet is moved into the solenoid and the magnet is moved out of the solenoid. Current produces when the solenoid is moved, keeping the magnet stationary. By keeping the magnet stationary, by moving the solenoid into the magnet, we can produce current. Which are the situations in which the current is increased? While increasing the number of turns of the solenoid. If we use strong magnet, that time also induced EMF or induced current increases. If we move magnet or solenoid with greater speed, that time also induced EMF or induced current increases. So, whenever there is a relative motion between the magnet and solenoid, there is a flow of current. On which instance will the magnetic flux linked with the solenoid be greater? In figure 3.p. When the magnet is moved towards the solenoid, isn't it? On which instance does a change in the magnetic flux linked with the solenoid occur while it is moving, isn't it? What is electromagnetic induction? Due to electromagnetic induction, electricity or current is induced in a solenoid whenever there is a change in the magnetic flux linked with the solenoid. This is known as electromagnetic induction. This phenomenon is known as electromagnetic induction. The current thus induced is induced current. The voltage thus induced is induced EMF. Which are the factors that affect the induced EMF? Number of turns of the coil, magnetic field or its strength, speed of motion of the magnet or the solenoid. What is electromagnetic? What is meant by electromagnetic induction? Whenever there is a change in the magnetic flux linked with the coil, an EMF is induced in the coil. This phenomenon is electromagnetic induction. Which are the factors that affect the direction of induced current in electromagnetic induction? Direction of magnetic field, direction of motion of the conductor. If we change the direction of motion, that time also direction of induced current changes. Direction of deflection of galvanometer needle changes. Okay, thank you.